Welcome to the Timeless Science. Every fundamental equation of physics allows time to move forward or backward with equal validity, yet every real process in the universe unfolds in only one direction. This contradiction is precise, measurable, and remains one of the deepest unresolved tensions in modern science. By the end of this episode, you will understand why physicists were forced to accept time symmetry, why reality violates it at every scale you can observe, and where scientific explanation currently reaches its boundary. The expectation that time should have no preferred direction did not come from intuition. It came from success. In 1687, working in Cambridge, England, Isaac Newton published the laws of motion that defined classical mechanics. Those equations describe how objects move through space, and they function identically whether time flows forward or backward. Reverse the direction of time, and the mathematics remains unchanged. This was not an accident. It was a structural feature. In 1865, at the University of Cambridge, James Clerk Maxwell unified electricity, magnetism, and light into a single framework. His equations described electromagnetic waves propagating through space with perfect time symmetry. They predicted radio waves, light, and electromagnetic radiation with extraordinary accuracy, yet they made no distinction between past and future. When physics entered the quantum era, this symmetry survived. In 1926, at the University of Göttingen in Germany, Erwin Schrödinger introduced the wave equation governing quantum systems. It allowed microscopic processes to evolve forward or backward in time with equal legitimacy. Nothing in its structure selected a direction. Physicists did not merely observe this symmetry. They depended on it. In 1918, also in Göttingen, mathematician Emmy Noether demonstrated that time symmetry is inseparable from energy conservation. Her theorem proved that if the laws of physics remain unchanged over time, energy must be conserved. Break time symmetry and energy conservation collapses. Entire physical theories lose coherence. This result transformed symmetry into necessity. Time symmetry was no longer optional. It was foundational. For decades, every successful physical theory reinforced the same message. The deeper scientists looked, the less reason they found for time to prefer a direction. At the most fundamental level, equations treated past and future as interchangeable. And yet, reality refused to cooperate. No macroscopic process has ever been observed to run backward. Heat never flows spontaneously from cold to hot. Broken objects do not reassemble. Biological aging does not reverse. Memory records the past and never the future. Physics demanded symmetry. Experience denied it. To understand where this conflict first became undeniable, we must now leave equations behind and turn to experiment, where time symmetry was not assumed but tested. For decades, time symmetry remained protected because it had never failed under experimental pressure. That changed in 1964 at Brookhaven National Laboratory in New York, when physicists James Cronin and Val Fitch performed a precise study of neutral kaon decay. Their experiment was designed to test whether certain particle processes behave identically when the direction of time is reversed. They did not expect a failure. They found one. Neutral kaons are unstable particles that decay into lighter products through well-defined channels. Cronin and Fitch observed that when these decays were analyzed under time reversal, the probabilities did not match. Certain transformations occurred more frequently in one temporal direction than the other. This asymmetry was small, but it was unambiguous. Time reversal symmetry was violated. The result was not statistical noise. It was repeated, confirmed, and quantified. In 1980, Cronin and Fitch were awarded the Nobel Prize in Physics for the discovery. More importantly, the finding forced physicists to confront a fact that equations alone had concealed. Time symmetry was not exact. The violation was later understood as part of a broader phenomenon involving charge and parity symmetry breaking in weak interactions. In particle physics laboratories across the United States and Europe, including experiments conducted at CERN in Geneva during the 1970s, Similar asymmetries were measured in related systems. Time, at the most fundamental level of particle behavior, showed a slight preference. But this discovery created a deeper problem than it solved. The observed violation was extraordinarily small. Its magnitude was nowhere near sufficient to explain why macroscopic reality is overwhelmingly irreversible. The decay of a kaon does not explain why heat flows in one direction, why stars burn fuel without reassembling it, or why memory never runs backward. Particle physics had revealed a crack in time symmetry, not its cause. This distinction mattered. The arrow of time we experience is absolute. It governs chemistry, biology, geology, and cosmology. It operates with certainty, not probability. A microscopic asymmetry buried in rare particle decays could not account for such dominance. By the late 20th century, physicists faced an uncomfortable conclusion. Time symmetry was not universally valid, but its violation was too weak to explain reality as we know it. The arrow of time could not be explained by particle physics alone. The problem had shifted. If irreversibility was not enforced primarily by fundamental forces, then it must emerge elsewhere. The next place physicists were forced to look was not motion or decay, but information itself, where direction is not optional but unavoidable. To understand why reality never allows time to reverse, we must now examine how information changes physical systems in ways equations alone cannot undo. The arrow of time becomes unavoidable the moment information enters a physical system. This insight did not come from philosophy but from engineering. In 1961, at IBM's research laboratory in Yorktown Heights, New York, physicist Rolf Landauer established a principle that permanently linked information to thermodynamics. His results showed that erasing information is a physical operation. It requires energy and necessarily produces heat. Information loss increases entropy. This was not a metaphor. It was a constraint. Landauer demonstrated that computation, memory, and measurement are not abstract processes layered on top of physics. They are physical transformations of matter. When a system records a result, its microscopic configuration changes in a way that cannot be perfectly undone. Time acquires direction because the system remembers. For decades, this principle remained theoretical. That changed in 2012, when experimental physicists at the École Normale Supérieure in Paris directly tested Landauer's limit using nanoscale memory devices. They measured the minimum energy required to erase a single bit of information and confirmed Landauer's prediction with high precision. Information processing was shown to have unavoidable thermodynamic cost. This result explained something particle physics could not. It explained why memory points backward. Brains, computers, and measuring instruments encode the past by irreversibly altering physical states. A measurement does not merely reveal a result. It creates a record that cannot be removed without consequence. Time, in this view, advances because information accumulates. But this explanation introduced a new tension. If the arrow of time arises from information processing, then it depends on systems interacting with environments. It is not written directly into fundamental equations. It emerges from correlations, records, and loss of reversibility at the level of knowledge. This tension became impossible to ignore in cosmology. In 1973 at Princeton University in New Jersey, Stephen Hawking demonstrated that black holes emit radiation due to quantum effects near the event horizon. This radiation appeared thermal and random, implying that information falling into a black hole could be permanently lost. If true, this would represent absolute irreversibility at the deepest level of spacetime. The implication was severe. If information is destroyed, quantum mechanics fails. If it is preserved, the arrow of time must arise without true loss. In 2019, the Event Horizon Telescope collaboration, operating across multiple United States observatories, produced the first direct image of a black hole's shadow. The observation confirmed the physical reality of event horizons, but it did not resolve whether information escapes or vanishes. Information theory explained why time feels irreversible. Cosmology raised the possibility that irreversibility is fundamental. To determine whether time's arrow is enforced by nature itself or emerges from physical limits on knowledge, we must now confront the boundary where modern physics stops providing answers. By the early 21st century, physics had narrowed the problem to a precise boundary. The laws permit time reversal in isolation. Reality forbids it in practice. The reason lies not in a single broken symmetry, but in how physical systems become irreversibly correlated. In 2021, at the Massachusetts Institute of Technology in Cambridge, researchers studying quantum thermodynamics demonstrated that while microscopic equations remain reversible, interactions between systems rapidly spread correlations into the environment. Once information about a system leaks outward, reversal becomes physically inaccessible. The equations still allow it. Reality does not. This result formalized a long-suspected principle. Irreversibility is not enforced by force. It is enforced by structure. When a system becomes entangled with its surroundings, restoring a prior state would require controlling every correlated degree of freedom. That requirement grows exponentially and becomes impossible in finite time. Time symmetry survives only in systems that are perfectly isolated. No macroscopic system ever is. This explains why the arrow of time dominates chemistry, biology, and cosmology without needing a strong fundamental violation. The universe does not reverse because it cannot gather back what it has already distributed. Information disperses, correlations multiply, and reversal becomes unreachable, even though no law forbids it outright. Physics has therefore reached a clear limit. We understand why equations tolerate reversal. We understand why real systems never exhibit it. What remains unknown is whether the arrow of time is fundamental to spacetime itself or emerges entirely from initial conditions and environmental complexity. Cosmology sharpens this uncertainty. If the early universe began in an exceptionally low-entropy state, as inferred from observations of the cosmic microwave background measured by the Wilkinson Microwave Anisotropy Probe at NASA in 2001, then the arrow of time may reflect boundary conditions rather than laws. The universe started ordered, and everything since has been consequence. But if future theories reveal unavoidable information loss at the deepest level, then time's direction may be written into reality itself. At present, physics cannot decide between these possibilities. What it can say with confidence is this: time reversal is permitted on paper. It is forbidden in experience. The gap between the two is not ignorance. It is the price of interaction. Time advances because the universe cannot isolate itself from its own history. Goodbye. Thank you for listening. Perhaps, see you in the next frame of understanding.